Have you ever stopped to actually wonder how we control the immense hidden energy pulses of a massive AI data center? We're talking about facilities consuming literally gigawatts of power. Every single rack, every high-performance GPU, and every heavy-duty cooling system is just drawing incredible amounts of electricity. Measuring, monitoring, and managing these massive power loads in modern AI factories, well, it's honestly one of the most incredible operational challenges of our time. It's this whole invisible world of energy. And today, we're going to crack it wide open and make it visible. Welcome back to The Explainer. Today, we're exploring the invisible world of smart energy management by taking a look inside the SuperCloud Composer Power Grid Console. If you're the kind of person who loves seeing how massive, complex physical infrastructure translates into really elegant digital solutions, you are in the exact right place. We're going to explore exactly how we monitor electricity, from the massive incoming utility grid all the way down to a single AI computing workload. Okay, let's dive into this. Here's our roadmap for today. We'll start with the Power Management Challenge, then introduce the SuperCloud Power Grid Console itself. After that, we'll track the specific power asset classes, follow the flow of energy from source to software, and finally, look at the physical magic of how CT clamps actually work. All right, part 1, the Power Management Challenge, or as I like to think of it, AI's energy hunger. Listen, the modern AI factory is just a completely different beast compared to the data centers of the past. Today, every single asset class drawing power absolutely must be tracked. We're talking from the massive utility feed right down to the specific GPU computing your workloads. Actually, scratch that. It's more like we aren't just plugging things into a wall and hoping for the best anymore. The sheer volume and density of these components mean that managing this complex power draw isn't just some nice-to-have feature. It's a critical operational risk. If you don't know exactly where the power is going, you can't optimize your facility. And more importantly, you can't prevent hardware failures or catastrophic overloads. Moving on to part 2, the SuperCloud Power Grid Console, essentially the central nervous system of the operation. Now, what's really interesting about this is exactly where the capability lives. This is where the invisible flow of electricity becomes a manageable, highly visible asset. The Power Grid Console is a dedicated, brand new module built right into the broader SuperCloud Composer Advanced Software Suite. It sits seamlessly alongside your compute, network, topology, and cooling infrastructure monitoring. It's basically acting as a live, real-time control layer for the entire AI data center's power ecosystem. Before we get into how we capture the raw electrical data, let's ground ourselves in what the end result actually looks like for a user. What you get is an incredibly detailed rack-level telemetry view inside the software. You can physically see the racks, their layouts, and their live status. This is the interactive interface that data center operators use to monitor the beating heart of their facility, taking all that complex math and turning it into something immediately readable. So what exactly does this console let those operators do? By pulling in data from all over the facility, it acts like a digital sixth sense. It tracks exactly how much power is available versus how much is actually being consumed. It pinpoints peak loads, identifying exactly which racks or cooling systems are drawing the most juice. It finds hidden spare capacity, identifies if a breaker, a PDU, or a feed is at risk, measures overall energy efficiency, and crucially gives operators the hard data they need to know exactly when to shift, limit, or prioritize workloads. Okay, part 3, tracking power asset classes. Let's do a macro to micro zoom. We're going to go on a rapid-fire visual breakdown starting from the outside in. At the absolute macro level, we have the primary power feed. This is the massive incoming utility grid connection, or maybe an on-site generation source. This is where all the immense energy for our AI operations first enters the story. So naturally, it's the very first asset class we need to measure. Moving one step closer into the facility, we hit the substations and transformers. You see, the immense raw power coming from the utility grid is far too intense to just plug a server rack into. Transformers step that incoming utility power down into a safe, usable facility voltage. The console pulls data from right here to ensure that step-down process is stable. Keeping up the pace, the power then flows through breakers and circuit protection. These are critical defensive checkpoints. They protect the main feeds, the remote power panels, the rack distribution units, and ultimately, your extremely expensive IT equipment from surges or faults. Monitoring at the breaker level is vital because it lets you identify localized hardware risks before they can take down a whole cluster. But hey, we absolutely cannot forget this incredibly crucial piece of the puzzle, the cooling systems, or CDUs.
The IT equipment isn't sitting in there alone. High-density AI GPUs get incredibly hot, and the liquid cooling systems, pumps, and cooling towers required to keep them running, well, they consume massive amounts of power themselves. This represents a completely distinct and totally vital tracked asset class in our infrastructure journey.
Which brings us to part 4, flow, source to software. Let's see how this builds. Now that we know the physical players involved, how does that physical energy actually translate into digital data? Let's trace the sequential journey of a single watt of electricity. It starts at step 1, the power source, like our utility ingress or a battery backup. Then it moves to step 2, power distribution, through substations, breakers, and bus bars. Step 3 is rack power via smart PDUs. Step 4 is the actual consumption by the IT racks and the liquid cooling load. And finally, step 5, that physical consumption is captured by meters and turned into telemetry and software data within SuperCloud Composer. This straight line creates a single, unbroken view of power usage.
And finally, part 5, how CT clamps work, the invisible sensor.
But how does the software actually know this? You might be wondering right now, how on earth do we measure invisible electricity inside thick, heavily shielded cables without, physically cutting them open to intercept the power? The answer is an ingenious little physical sensor called a CT clamp, like the Bentus eGauge systems used in these setups. A current transformer, or CT clamp, physically opens up and just snaps around a power cable. It doesn't even need to be wired directly into the electrical flow. Instead, the clamp simply senses the magnetic field that is naturally created by the current flowing through that conductor. By carefully measuring that external magnetic field, it precisely calculates exactly how much current is passing through the cable inside. It's brilliant. And because these clamps are completely non-invasive and so easy to install around existing lines, they are mapped all over the facility. They provide live, granular visibility at literally every critical junction. We are talking about mapping clamps on the grid incoming feed, the UPS output, the battery inverter feed, the dedicated cooling circuits, all the way down to the PDU or rack feed. This creates a highly dense web of sensors, constantly feeding real-time energy data back to the centralized software. So, the absolute crucial point is this. Why go through all this meticulous trouble to clamp every different type of cable in the building? Well, it's primarily for PUE, or power usage effectiveness. This is the ultimate grading metric for a data center. By having specific clamps dedicated to the cooling systems and separate clamps dedicated to the IT racks, the software can explicitly separate the total power the facility uses from the power used just for computing. Without that distinct separation, you just cannot accurately calculate PUE, which means you can't prove to the market how efficient and optimized your AI factory truly is. Which leads us to a massive, provocative question to end on. With this level of live power, visibility, scaling from the incoming massive utility grid all the way down to the individual AI workload, how will this central nervous system change the future of data center optimization? We're moving away from simply keeping the lights on to a world where we dynamically shift, limit, or prioritize AI workloads in real time based on live grid availability and cooling efficiency. It's a completely new, absolutely fascinating era of energy-aware computing. Thank you so much for joining me on this explainer. Keep seeking those structured answers, and I'll catch you next time.